Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from D-Wave Systems. We have Colin Williams. He is the Director of Business Development and Strategic Partnerships at the company. Colin, welcome to the show today.
Oh, hi, Rich. Thank you very much for inviting me.
Well, thanks for coming on, Colin. You know, we've seen a lot in the press lately about quantum computing and D-Wave, but I thought this would be a great opportunity to kind of see what you guys are up to. So why don't we just go into your slides, and then we'll follow that with a Q&A.
Okay, that sounds fine. So I was going to talk to you today about some thoughts we've had recently about how we might integrate our quantum computer with more mainstream HPC systems. So that's what I'd like to talk about. So if we look at the first slide, I'm going to give you a brief background on D-Wave systems, and then move into what are quantum computers and how are they different from regular HPC systems. And then talk a little bit about D-Wave's approach to quantum computing and the rationale behind us taking that particular approach over others. And then talk briefly about the current product, the D-Wave 2. We're very proud of this machine. And then some ideas on how to integrate that machine into mainstream HPC systems. So D-Wave Systems is a privately owned company, headquartered in Vancouver and Palo Alto. We just opened an office in the Washington, D.C. area as well. We are funded by some really top-tier investors. The most recent additions have been DFJ, Goldman Sachs, Inquitel, and Jeff Bezos' personal investment fund. And we're also backed by GrowthWorks, Business Development Bank of Canada, Harris & Harris, and Kensington, and BC Investment Management Corporation. So we have quite a lot of investors behind us, and we have a good runway of funding if we need more funding in the future. What we offer is quantum computing systems built specifically from superconducting processors. We have about 100 employees today, of which 27 or so are PhDs, 18 are engineers, so quite high-tech heavy. We have more than 100 issued U.S. patents, which is really large for a company of our size. And although there's a popular meme on the internet that D-Wave doesn't talk about what we're doing, we actually have over 60 peer-reviewed publications in print. People can really understand, if they want to read about our technology, there's a lot out there people can go to look at. And one of the things I think that's made D-Wave so successful in terms of developing this quantum computing technology is we really have a unique infrastructure. We have everything we need under one roof to build a quantum computer. We have people who are experts in designing superconducting electronics, other people who are experts in fabricating superconducting devices, testing them, developing systems to go around them, and even software for programming them. And that's really been a key to our success, that we've had this little mini Manhattan project, essentially, of all the expertise co-located to put this amazing machine together. And I think a testament to how innovative D-Wave is, at the end of last year, IEEE Spectrum ranks D-Wave the fourth most important company in terms of patent power for computer systems. So we beat out companies such as Dell, NEC, Cray, Silicon Graphics, which is really, for a company of our size, is really quite remarkable. We also are working with some really top-tier companies and organizations around the country. We are in the defense sector. We're working with Lockheed Martin, and we are funded by Inquitel, which is the investment arm of the CIA. With Web, we have a relationship with Google, and the national labs, we have a relationship with NASA, particularly the NASA Ames Research Center, which is a new machine recently deployed in a quantum AI lab that's based on D-Wave technology. And we have another machine at the University of Southern California under funding from Lockheed Martin. So we're really in the aggressive stage of ramping up our business now and really putting deals together with top-tier players in all these different vertical sectors. So I want to talk a little bit very briefly about what are quantum computers and how they're different from HPC systems. So quantum computers are devices that harness quantum physical phenomena that simply aren't available to conventional computer systems. So the four most prominent ones that we use are these four here: superposition, entanglement, co-tunneling, and non-determinism. So let's take a look at each of those in turn. So superposition, if you think of the memory of your computer being represented by a bit string, then in a conventional computer, that bit string can be in one configuration at a time. But on a quantum computer, it can be in a blend, or what's called a superposition, of all 2 to the power n configurations you can write in n bits at the same time. Now, quantum mechanics limits our ability to see these different components of superposition individually, but you can create a state that represents essentially all possible inputs to a program at the same time, and then act on them collectively. The next phenomenon is one called entanglement, and this is a very interesting, quintessentially quantum phenomenon. Usually, if you think of a computer memory, and you look at one subset of the bits in that memory and you do some operation on those bits, you don't usually expect that operation to have any kind of side effect on the bits that you didn't touch. But in a quantum computer, if the state of the quantum computer is entangled, doing an operation on one subset of the qubits can have a side effect on the other qubits that you didn't touch. And this property can be exploited to devise new kinds of algorithms that work in ways that are quite unlike the way classical algorithms work. A third phenomenon that we use a lot is what's called co-tunneling. And this allows a quantum computer to change from one collective state to another collective state, essentially without passing through the intermediate states that you go through. So we just sort of change collectively from one state to another state. And then finally, non-determinism, that is true randomness. Because we're using quantum mechanics at its core, we have true random numbers in our system. We don't have pseudo-random numbers. And we make use of all these 4 phenomena in our actual quantum computer. So what makes these quantum computers interesting? Well, I always like to say that there's 2 reasons for this. So one is pragmatic and one is more philosophical. So pragmatically, quantum computers allow us to solve problems in fundamentally new ways that have the potential to beat the best we can do classically solving the same problem. So in some cases, we can actually prove you can get an exponential speedup. So for example, in factoring composite integers or simulating quantum physical systems or doing certain problems in quantum chemistry, that it's known that quantum computers have the potential to be exponentially faster than the best algorithms we've come up with so far for doing these things on conventional computers. There's a much bigger class of problems, though, in which we see polynomial speedups. And the most famous algorithm in this class is Grover's algorithm for doing unstructured quantum search. And a few years ago, I extended that with Love Grover. I wrote a paper with him showing that you could extend it to structured search problems. The latter are a lot more interesting because this covers this class of problems called NP-complete and NP-hard problems, which are really pervasive problems in sort of mainstream business computation and industrial computation. Now, that's the sort of pragmatic reason, basically faster algorithms than you can have classically for a quantum computer. But there's another reason that motivates a lot of people at D-Ray, and actually the philosophical difference between classical computing and quantum computing. So David Deutsch, who is really the father of the field of quantum computing, he said this really well. He said that quantum computation will be the first technology that allows useful tasks to be performed in collaboration between parallel universes. Now, so most computer scientists and HPC people, when I say that to them, they look at you like you're crazy because this sounds like it's science fiction. But people who are in mainstream quantum physics, take the reality of these parallel universes quite seriously. And it's quite a reasonable statement that David Deutsch has made here, and I think it really amply illustrates just how different a quantum computer could be from a conventional computer. To think that we're actually doing engineering now on these different parallel universes. I think that's really exciting, and it gets a lot of people at D-Wave excited to think about that. So what is the significance to high-performance computing of harnessing these quantum mechanical effects? So I've given this some thought, and I've been characterizing this in the context of the quest to build an exascale high-performance computer. And if you think about the 5 main metrics for an HPC system, is concurrency, robustness, power, storage, and speed. We can think, how does quantum computing affect each of those dimensions? So let's take a look at concurrency to start with. So a typical exascale HPC system will probably have something of the order of 100 million cores and 10 billion threads going on in parallel. But just one 512 qubit quantum core has 2 to the 512, which is equivalent to about 10 to 154 virtual threads in superposition, all going on at the same time. But of course, the price you pay is quantum mechanics limits your ability to read these threads individually. But there's a huge difference. Secondly, in terms of robustness, it's generally understood that if we want to make an exascale high-performance computer, we're going to have to make the components from the chips a lot smaller. And when you make those components smaller, you're going to use reduced operating voltages, narrower channel widths in your devices. And those devices are therefore going to become intrinsically a lot less reliable. So it's generally believed that we're going to need to move to a new, more probabilistic programming style when we get to an exascale HPC system. But the good news is that quantum mechanics has probabilistic programming built in for free, because quantum mechanics is, in principle, non-deterministic. When you make measurements of the quantum system, you can't predict ahead of time what answer you're going to get. And quantum mechanics gives us this intrinsic true randomness for free. It also means that the kind of quantum computer we're making has a sort of natural, graceful degradation property built into it, so that if you don't get, for example, the true optimal solution to your problem, you will probably, with high probability, get a very close to optimal solution. So it's a nice, smooth degradation. Third characteristic that's really different is the power consumption. So a typical exascale computer today, we expect to consume something like 25 to 100 megawatts. And this is actually a problem for locating HPC centers of that size, because not many locations can support that kind of power demand. By comparison, our quantum computer today consumes 15 kilowatts. And remarkably, almost all of that power is for running the dilution refrigerator, which we need to make the chip really, really cold. It actually takes close to zero power to compute something of the order of milliwatts to actually do the quantum computation, and kilowatts to run the fridge to make the chip cold enough to turn on these quantum effects. And in classical HPC systems, most of that power consumption is due to moving data around. In our quantum computer, there is no data movement. Another characteristic would be storage. A conventional HPC system might be something like 100 petabytes capacity. But in a quantum computer, because we're exploiting all these parallel universes, if we had a quantum computer made of just 300 qubits, then that would be able to represent, quite literally, a configuration of 2 to the power 300 different states at the same time. And that's more particles than there are in the known universe. So we have the potential to represent things explicitly, which are way beyond what we can represent classically. And then finally, speed. By definition, an exascale high-performance system is going to run at 10 to the 18 floating point operations a second. But ironically, although the quantum computer has the potential to be very fast, it doesn't do floating point operations, so it actually runs at 0 flops. So it's a very big distinction there. So for all these reasons, does it mean that quantum computers are going to make HPCs obsolete? And the answer is probably not. And the reason is they're suited to very different kinds of tasks. So HPCs are typically good at problems such as computational fluid dynamics, molecular simulation, weather forecasting, nuclear weapons modeling, things like that. And quantum computers are good at different kinds of problems: discrete combinatorial optimization, artificial intelligence, machine learning, and Monte Carlo sampling, things like that. But together, we believe that these two devices can be used in concert. And I know the media often likes to portray it as a horse race between quantum computing and HPC systems. But at D-Wave, we actually see it as potentially a lot more synergistic. I mean, we're used to thinking of HPC systems today that are built out of CPUs and GPUs. In the future, we foresee the day when we would add a QPU, a quantum processor unit, to the mix, and just another resource for HPC. So what exactly is D-Wave's approach to quantum computing? There are many different ways you could go about making a quantum computer. We picked one which is called quantum annealing. And the way quantum annealing works is that the different solutions to your problem can be thought of as defining an energy landscape in which the height of the landscape corresponds to the quality of the solution, and higher the landscape, the worse the solution is. And the x-axis, the horizontal axis, corresponds to different bit stream configurations. So as you look at this diagram, you see that this landscape has an irregular form, and the best solution would correspond to the lowest point on this landscape. Now, what's remarkable is that every single computer in human history so far has been confined to run algorithms that effectively explore the surface of this energy landscape. That's all they can do, no matter what kind of computer it is, no matter what kind of algorithm it is. You've been confined to exploring the surface of these energy landscapes. For the first time, what the quantum computer running this quantum annealing algorithm allows you to do is to have this additional property of being able to tunnel through the hills from one valley to a lower valley next door. And this is the fundamentally new resource, this co-tunneling property that we're exploiting in our quantum computer to solve certain problems faster than you can do classically. So what's the product we're offering today? This is what it looks like. This is the D-Wave 2 quantum computer. This is a system being installed at a customer location. If you look at the center of the photograph, you see two kinds of skins. There's a black outer skin and a silver inner skin. That silver inner skin is actually an important part of the computer. It's a shielded room that excludes all radio frequency interference from the outside. We need to get rid of all radio frequency noise for the machine to work properly. On the right-hand side of the picture, you see three 19-inch racks that contain servers that will be used for programming the quantum computer and communicating with the outside world. And also, they control the cryogens, the gases they use to actually run the solution refrigerator. And that blue oil drum-looking object in the center of the picture, that's the outer skin of the dilution refrigerator. And the people in the picture give you a good sense of scale, that the footprint of this thing is about 10 feet by 10 feet by 12 feet high. So if you're looking at a blue oil drum in the last picture, it looks silver in this picture. That's the outer skin of the dilution refrigerator. That fridge consumes about 15.5 kilowatts, the fridge plus the servers in the 19-inch rack. And that power demand is going to remain more or less constant as we scale up to thousands and thousands of qubits, because as I said before, almost all of that 15.5 kilowatts is going to run the dilution refrigerator. It actually takes almost no power to run the quantum computation by comparison. And that fridge has the capacity to hold a chip which is significantly larger than one we have today. So if you were to open that outer skin of the dilution refrigerator and look inside, you see this object which looks like an inverted ray gun. That's actually a cryostat. And the purpose of that cryostat is to step down through a sequence of temperatures that take the electronics from room temperature all the way down to the very bottom of the cryostat, which is operating at 20 millikelvin. That is 0.02 Kelvin. And so everything connected to that very bottom plate, which weighs about 10 kilograms of metal, is at an operating temperature of 20 millikelvin. And at the very bottom of that is where the actual quantum chip sits in the very coldest part of the fridge. So this environment is very exotic. It's about 150 times colder than interstellar space. And it contains a very, very weak magnetic field because we have to null out the magnetic field across the chip to less than 1 nanotesla in each dimension. So that makes the magnetic field 50,000 times weaker than the Earth's field. So the operating environment of this quantum chip is extremely exotic. It's one of the coldest, most isolated, most radio frequency quiet, most magnetically quiet regions in the known universe. So we've been developing a sequence of processes over the last 10 years or so, and we've maintained a remarkably a fast rate of progress. We've been doubling the number of qubits in the processor each year and releasing a new processor class every 2 years, which is actually a faster growth rate than Moore's law. And the current processor is 512 qubits. Next year we expect to have internally a 1,024 qubit chip, and then we'll be releasing a 2,048 qubit product in 2015. And you should realize that what the purpose of the 512 qubit chip is to find the best bit string based on 512 bits that minimizes some objective function. So the possible number of configurations is 2 to the 512. When we go to a 2048 qubit chip, the number of possible configurations will go to 2 to the 2048, which is just mind-bogglingly large. And you often see a lot of chatter in the media about the D-Wave chip, does this, that, or the other. One thing I think we need to point out is that there really isn't any such thing as the D-Wave chip. We design and iterate on our design at such a high frequency where we have something of the order of 6 to 8 complete design innovations per year. And every time we release a new design, it's because we're putting in some new components that attempt to improve some performance of the design before. So it's almost inevitable by the time you're reading anything about a D-Wave processor, the processor we have in-house is substantially different from the one you're reading about. And that's certainly true today, that the next generation chip is already well into development. So if you to look at the chip under a microscope, this is what you would see for the 512 Vesuvius processor. The actual quantum chip is the rather dull square on the left-hand side of this figure. On the right-hand side, there's superconducting classical electronics that's used for locally programming the quantum chip, and also some test structures, because when you make the quantum chip, it's made from 6 different layers of niobium, and if you're looking under a microscope, you only see the top layer. So when we make a chip, right next to it, we make each layer exposed, so that if we get a wafer back that's not performing as we would like, we can probe the individual layers and the components to see which one is not functioning perfectly. So if you sort of zoom in on just the quantum chip, you see that it's architected as an 8 by 8 array of a repeating unit cell. And on the top right of this diagram, there's a blow-up of what the physical structure of this unit cell looks like. So the red rectangles correspond to loops of niobium metal containing a Josephson junction. They serve as our qubits. And if the current is flowing in one direction, that generates a little magnetic field that we can think of as a tiny spin, which is spin up. And if the current is flowing in the opposite direction, that generates a little magnetic field that we can think of as spin down. And because these devices are operating in this really exotic regime of ultra-low temperature and low noise, they can enter this quantum state, which is a combination of spin up and spin down to varying degrees at the same time. So where 2 of these red rectangles cross, we actually put a coupler. So not only can we put a bias on each qubit to make it want to be more spin up or spin down, we can put a coupling on certain pairs of qubits to make them want to be either aligned or anti-aligned. So if you look at the bottom left of the figure, what you see is a sort of logical layout of the qubits in which, instead of being these extended rectangular structures, the qubits are now represented as dots. And you can think of those dots as little spins that can be either spin up or spin down, and the edges in that graph correspond to the spins that we can connect together. We can make those connections want to be aligned or anti-aligned. So the fundamental way you program this device is you give a bias up or down to some degree to each of the qubits, and you specify a coupling, aligned or anti-aligned, to each of the qubits connected in that graph. Now, what's really important about that graph is not planar. And the critical reason that's important is if you look for the configuration of spins up or down that minimizes the energy of that graph. If that graph was a planar graph, we know we can compute that minimum energy configuration efficiently on a classical computer. But when that graph is a non-planar graph, we know that we can't compute that minimum energy configuration efficiently. In fact, it's an NP-hard problem to find the minimum energy configuration. So to program the device, we're basically exploiting the fact that there are known efficient mappings from one NP-hard problem to another one, so that given a particular problem we want to solve, we map it to the NP-hard problem that the chip solves natively, and that's how we basically program the device. So the programming languages, the good news for most people in HPC is you don't need to know any quantum physics whatsoever to program this device. All you have to do is pass a matrix representing the biases and couplings in the graph to the chip. And you can pass those matrices currently in 3 programming languages, Python, MATLAB, and C or C++. And we can easily add other programming interfaces to your programming language of choice. So let's turn finally to how we might use this quantum computer in conjunction with high-performance computer systems. So HPCs excel at certain kinds of computations, particularly large-scale numerical simulations, computational fluid dynamics, magneto-hydrodynamics, things like that. Quantum computers excel at discrete combinatorial optimization, finding the bit-string configuration that minimizes some energy function. So the idea we had at D-Wave is, can we use these 2 technologies in concert, HPC in collaboration with quantum computing for something like engineering design optimization? So the problem we have in mind is, suppose you want to design some engineering artifact, and you can represent that design by a bit string. Then the various designs can be scored by converting the bit string into a model and then running a simulation of that model on an HPC system. And at the end of the day, the HPC computer comes up with some kind of number that scores how good that design is. And the goal is to find the bit string that gives you the best performance, meets the design criteria to the best degree you can. So in this scenario, the job of the high-performance computer is to map a bit string to a design, simulate the design, score the result, and then send that score back to the quantum computer. The quantum computer's job is to use the sequence of pairs of bit strings and scores coming back from the HPC, and then use that stream of samples of the energy landscape to tweak the biases and couplings that change the program the quantum computer is running. And then when you tweak those biases and couplings so that you reproduce as closely as possible the distribution of samples you're seeing from the HPC system, you then rerun the quantum computation with the new biases and couplings, come up with a new bit string, which you feed to the HPC system, which it then simulates again. And we can basically, once we've come up with a new set of biases and couplings, we can draw something of the order of 10,000 samples a second from this new energy landscape. And then the HPC system can convert those designs into models and then simulate them. Now, the idea then is we iterate this process where the HPC system is simulating the models and the quantum computer trying to learn the structure of the landscape coming from the HPC system until we need to find a design that meets all our criteria. So the basic scenario is that we're using the quantum computer and the HPC system together to allow faster convergence on an optimal design that would be attained by using the HPC system on its own. So if we can achieve this, it means that we would avoid unnecessary HPC cycles and power consumption, which of course the power consumption of an HPC system is monstrous potentially. And it therefore increases the availability of the HPC system for running other computations. And this whole process from the testing we've done so far seems to work really best when the cost of running that HPC simulation is extremely high, because then the benefit from the avoided simulation is all the greater. And we call this idea quantum accelerated high-performance computing. So why does this work? Well, if you imagine you're at an intermediate point in this design process, you've found some bit string corresponding to some design, which you think is pretty good. And the question the computer faces is, what bit string should I try next? So using the classical methods, you might try flipping one bit at a time, 2 bits at a time in this bit string to explore the local neighborhood of the bit string corresponding to a slightly different design. But with the quantum computer, you're effectively able to explore a much bigger neighborhood in one step than you can classically. And potentially that can take you off in a design direction you wouldn't have found doing things purely classically. So I'll give you an example of what we've done so far, a study of using this. We've applied it to coming up with a plan for radiotherapy for cancer patients. So the idea is you want to find a set of orientations in which you inject radiation and a set of intensities for that radiation into a patient so that you can deliver a lethal dose of radiation where all the beams intersect, while at the same time minimizing collateral damage to the tissues the radiation has to pass through. And so for each different configuration of the beams and their intensities, there's a model of how radiation propagates and scatters through human tissue and how much energy it deposits along the way. And the idea is to find the treatment plan, the configurations of intensities and angles to shoot the radiation in that delivers the lethal dose while minimizing the damage to the tissue. And what we found so far, the people we were working with on this, they were using a taboo solver for doing this optimization classically. And by swapping in the quantum computer for the taboo solver, the objective function that we were trying to minimize was able to minimize it down to a number 70.7 using the quantum computer compared to minimizing it to only 120 for the taboo solver. And the quantum computer ran about a third the time because it made far fewer calls to the radiation transport simulation. So we think that this is a really exciting direction in which to push quantum computing technology, because we're no longer in a position where we see ourselves as fighting and competing with HPC, but we see quantum computing as potentially a new tool in the arsenal of the HPC designer. So that's all I wanted to talk about today. I greatly appreciate the opportunity to speak to your audience. We see quantum computing as really a new resource for HPC. The technology that D-Wave has been developing has been coming along at a breakneck speed. We've been doubling the number of qubits every year, which is an even faster rate of growth than Moore's law for transistors. Early next year, we expect to have 1,024 qubit experimental system in-house, which we'll be doing our internal testing and development on. And we see a lot of potential uses for this technology. I've talked about one today using quantum computing in conjunction with HPC. But in general, we see this kind of device as being ideally suited to solving problems in control optimization, engineering, design optimization, artificial intelligence, machine learning, and potentially Monte Carlo sampling too. So right now, we're looking for some early adopters in the HPC world to try and get some projects together which demonstrate using the quantum computing in different kinds of applications by connecting it to an HPC system. So thank you very much for your time. Next slide. And I greatly appreciate the invitation to speak to you today.
Well, thanks for that, Colin. A question. I was talking to the folks at NASA Ames, who of course have one of your machines in the basement there, and they were telling me they're working to connect it to the Pleiades supercomputer, which is something like 150,000 cores or something. In that hybrid model you described, with the two working together, how much faster is potentially is the quantum computer at doing its part of that versus what a giant supercomputer could do on that particular kind of problem?
Well, we have limited data yet. This is still the early stage of exploring this hybrid use of a quantum computing in conjunction with a high-performance computer. But from the radiation transport example we gave, we were able to shave off 2/3 of the time. So we were able to get the optimal configuration as good as in fact, a better optimal configuration than the classical computer found using to do in 1/3 the time that the classical system was able to compute it. So that kind of order of magnitude is something I think should be very attainable. The more expensive the HPC simulation, the bigger the potential benefit is, because then every time you avoid having to run the HPC simulation one more time, it could be a very large time saving. So I don't think it's actually possible to give you a single number that characterizes what the speed up could be potentially. It's going to be very application dependent and vary from case to case. But from what we've seen so far, it has potential to be very large indeed.
Yeah. So I was curious about the cooling technology, Colin. I hadn't come across this term of microkelvin before, right? But less than 1 degree Kelvin. Was that a huge obstacle as you guys developed this technology in terms of engineering? I mean, delivering a space that was that cold and that shielded?
I would say no. I'm sure our low temperature physicists would howl at that and say it was very difficult. But the technology we use for making the chip that cold is commercially available by several different vendors around the world, because these devices have been developed for use in physics experiments for a very long time now. What has changed with D-Wave is that the current market in low temperature dilution refrigerators was built for physicists to use in experiments that might run for maybe 6 weeks at a time. But of course, to make a functional computer, we want this computer to be up and running for all the time, or as close to all the time as we can get. So when we get a dilution refrigerator in from the vendor, the first thing we have to do is to do some sort of retrofitting on the design that would specifically make the dilution refrigerator function for very long periods of time without any kind of interruption. And all of that innovation is something we've done in-house at D-Wave. The other thing we've done is, because we're essentially agnostic as regards which dilution refrigerator technology to use, we have dilution refrigerators from all of the vendors, and we understand a lot about the idiosyncrasies of each of them and how we need to modify the system to make it perform better for longer periods of time. So in-house, we have probably the world's best knowledge base of long-time operation dilution refrigerators of all varieties today. And I think that going forward, we actually have a lot of innovations we've come up with for improving ocean refrigerated technology. And our strategy is to actually tell those design improvement ideas to the vendors so the vendors can incorporate them into their fridges.
Well, great. Well, Colin, I guess the question comes to mind is, you're in business development. Have you looked at what is the potential market for this? I mean, there's only a few of these machines in existence today. Could you foresee a time when there might be, hundreds or even thousands of these devices out there?
Oh, absolutely. When we hit our stride and we start finding killer applications in different verticals, the market will just explode for these kinds of devices. And we could literally be talking about thousands and thousands of quantum computers around the world someday. As we get to that kind of scale of problem, we will be able to put a lot more investment into miniaturizing the system and the cooling technology. The D-Wave quantum computers of the future don't have to be the size that they are today. We will see a reduction in the scale of the devices going forward once we increase the market size beyond a certain factor. But potentially this market is enormous, because I've just talked about one particular application concept with you today, that is coupling an HPC system to a quantum computer. There are other applications that only use the quantum computer, and they would be, they each have large markets potentially on their own, such as doing Monte Carlo kind of sampling applications. That looks like it's a good match for this kind of technology too. And there's many, many ways you can exploit that commercially.
Well, along those lines, Colin, kind of a wrap-up question here. You said you are looking for partners. How does somebody engage with D-Wave if they want to kind of kick the tires on this and see if it's got potential for their application?
Well, we're a small company still. We're about 100 people. So we have to be very selective in who we partner with. And the most natural way to begin a relationship with someone is that they would contract with us to do some kind of joint proof of concept project. And then based on the successful outcome of that project, there would be a commitment to go forward to some kind of installation of the system thereafter. So HPC users who are thinking in that kind of framework would be good fits for us.
Well, great. Well, Colin, this has been fascinating, and I really want to thank you once again for coming on the show today.
Well, thank you very much, Rich, and thank you to your listeners for staying the course. I greatly appreciate the opportunity.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.